Yes. Yes. So the early versions of Spark were built on actors, but then they needed something extra that wasn't in the actor framework. So they went their way and they left the actors behind. Probably later on they regretted because the actor framework evolved even faster. And now it's following much more powerful frameworks than Spark. For example, Flink, Apache Flink, if you ever heard of it. Now it's powered by the actors again. So let's start. You all know Java, I believe, right? So this is a very what?
You can drag that out of the way too.
This is my mouse now.
Yeah.
Yes. Okay. So this is a data class. Very ordinary data class with a person, with a name, and address. And when you create it with a constructor person, you assign the values to the fields, and you say, welcome that person. The person object is constructed. And then you have a getter for each of these variables. Simple enough, right? Let's write exactly the same in Scala. Right. So, class. Good. The same. Private string name. Here you say private name of type string. So, a little bit of syntax difference. And instead of saying the person as a constructor, we use this. This is the constructor, how you define a constructor. And here are the getters, right? So it's one-to-one to Java, right? This is very simple. So it's easy for people from Java world to go to Scala world because they can just write Scala in Java style. Yes?
Is Scala JVM?
Yes. So all this was one design decision that they took, the Scala people took, to open up their world to all the libraries written in Java, because you can just use them. Now let's try to really get to the essence of Scala. So, yeah, so we'll try to take this one out, this string, as a constant. So here I define a val. Val means constant, var means variable. And I print the welcome note. Okay, first things first, some conventions. Parentheses, you don't need them. But you can have them if you really want to say a message. Meaning, if this is a mutator method, then you give them just to indicate to the caller that, hey, this thing will mutate the state. In our case, it's not a mutator, it's just a getter. So you can take it out. In that sense, actually, this and this, they look like fields. They don't look like a method invocation. Okay. The strings, the types. Yeah, well, this is a string. I said that. This is a string. I said that. So these getters get me strings. I don't need to say it again. Done. So this is the type inference system in Scala. Same here. Welcome note. Developed. I don't need to declare a string because obviously it's a string. More. Private. I don't want to say private. By default, it's private. If it's a field, it's private. This is the power of default. More. Yeah, these assignments, all this name, address, this dot name, this dot, I don't know what I can do now. One go. I can define the constructor next to the class name with the variables that I want to set in the constructor. That's it. It's done. And now I just print the welcome. Simple enough. It's getting more elegant, isn't it? This is what I like about Scala. I don't need to write more code. So this is what I have now. But look at this. Really, for every person object I need to create, I have to instantiate a string. That's a waste of memory. It's a constant. I don't need to have it like that. So it should be in Java. What should it be?
Static.
Static. Static. Good. This is how we do static. Every class has a companion object. That's what I call it. I define it as object, and it's a companion object. It's a single. And inside of it, I can define the welcome thingy. That's it. And as you see, this is now a method. And it has one thing to do is print the welcome note. And inside the person object, person class, sorry, I just person.12. That's it. How do you feel about Scala? Simple enough? Okay, that's good. Right. So this is how I define main classes in Java and Scala. Also, simple enough, the same thing. The same signature, actually. I use the same signature for the main. Public static void main. It's static because it's an object, and main args an array of string. It returns unit, which is in Java world void. Simple enough. Right. So what I want to show you now is that some tricks. So this is a data class, which means that it just encapsulates a bit of data, and I want to interact with it. No more, no less. There's no logic there. So what I can do, I can make it a case class. And case class is, think of it as, do you know Pascal by any chance? No. What about this Pascal? Okay. So it's a record. Case class is a record. It's a dictionary. Name of the attribute, value of the attribute. No more, no less. And that makes things a lot easier for me later to use. By just declaring it as a data class, as a case class, it makes things happen faster and more elegant. For example, I can do matching. Look at this. I say John is a new person of John my address. Good. Now I have John object. This is what I can do. I can say John match. If he looks like person with John first name, I don't know the address, then print John's address is the address. So here I did two things. I did match the name, and I did extract the address. I got something, and I said something, and I used it in a matching way. Default, not John. So only if the name is John, I deal with it. You can do this only if you declare it as a case class. That's why you see in the Scala applications, you see a lot of case classes, because I want to make it explicit that this is a data class. Then all the logic happens somewhere else, and they use pattern matching a lot. Simple enough? Questions? We move on. Now the actors. Right. So the actor models is yet another way of declaring things computable. So in a way, it's a framework like Turing machine, like lambda calculus. Now you have the actors. So every problem that is computable could be expressed in the actor model. This is the theoretical idea. You know Turing machine, how it works, right? So it's it was actually just to see if the brain is computable, the human brain is computable. That was the whole aim for it. Then the whole computer science came as a side effect. So they were trying to model the brain. And actors are not new, so it's not a new thing. So what I'm going to show you is the ACA framework, which is in Scala and whatnot. But this is very, very old, from 73. Oh, here, this guy. And I think he's still alive. I saw a lecture of him in 2018. Yes, he's a cool dude. Go look him up on YouTube. He has so many cool lectures. The first time the actors were overhyped is when Ericsson came out with Erlang. Erlang is all actors. So the building block of the language is actors. So every phone call you make, guys, is going through an actor system, no matter what you do, because Ericsson is pretty much on all communication systems. And they went out to Java for a couple of years, I think in 2005 or so, Ericsson, and they failed miserably, and they got back to Erlang completely. Like, yeah, no Java. Erlang will work. So why actors? I will explain later what actors are, but what is now the motivation? Why are we doing this? So this is concurrency course, right? And what is the source of all problems in concurrency? It's shared state. I would even go one step further. It's the problem with any programming language, regardless of being concurrent or not. It's the shared state. So if you can not share state, please don't. It's just a source of debugging complexity, bug problems, and so on. So they want to get rid of it. And you all did some concurrency multi-threading stuff. And you notice that the logic of concurrency, like initiating threads, waiting on something, and the business logic are kind of intertwined. So if I give you now a concurrent system, you will find it a little bit harder than usual to take out the business logic. Okay, what happens when I receive this message? And then what is other things that the classes are trying, or the objects are trying to coordinate over locks and whatnot. So they are kind of together. For us, in actors, the concurrency problem is a deployment problem. So now here's my business logic. Now deploy it in memory, in machines. I don't care. So the thing is, concurrency in one machine with shared memory is one beast. Now taking it out to different machines is a monster. So you see distributed systems they share a lot of the concurrency problems and more. And that's why they wanted something, when they built the active model, they wanted something that can generalize and can work in both cases, abstracted away from the engineer building them. What are actors? Please look at this. Are fundamental units of computation that embody processing, which is behavior, storage, which is state, and communication, which are messages. Behavior, state, and messages. What does that look like to you? What does that sound like? I'm sure you've seen it. I'm sure you did something with it quite some time. It's an encapsulation of behavior and state. What is?
Server.
Server. More? No. Go a little. Java. What is this? If I give you this question in an exam, what is this in Java? What object? Thank you. It's an object. No more, no less. Look at that. It's an object. You have methods, behavior, you have state, variables, and you have messages, which is invoking messages. Or even more explicit in Smalltalk, you have seriously sending messages. So that's an object. But there are some caveats. Now we're going to get to it. When an actor receives a message, so I have a message, what does the actor do? It can create more actors. It can send messages to actors, to other actors, or it designates what to do with the next message. Okay, this is kind of a fancy way to say it mutates its state. It designates itself on what to do with the next message. Right? So I change the state such that the next message has a new state. Or functionally speaking, I create another behavior. I will show you examples of both cases. But why is it different from OOP? Why the actors are different from OOP? What's so special? Every actor has an address. So you see here the encapsulation has a little bit more than behavior and state. You have the concept of an address and messages and mailbox. So you have an address, you have a mailbox of messages coming in. This one is absolutely crucial. An actor can process one message at a time, just one. Like what in Java world? It's a concurrency class, isn't it? What? what concept you have, guys? That
I guess a monitor.
a monitor, thank you. It's a monitor. It's a monitor with a mailbox. That's what an actor is. It's a monitor with a mailbox. It can just push messages down a queue and process them one after another. What else can you should have camera over there? No? All right. Another thing that you see here, it's kind of inherited from other systems. Everything in an actor system is an actor. Everything. Similarly to the mantra in Smalltalk, everything in Smalltalk is an object. Here's the same. Message delivery is best effort, and this is also crucial. In Java, you invoke a message, invoke a method on another object, you're sure it's going to be invoked. Here, it's best effort. We'll try. So the burden is shifted to the invoker, to the client, to make sure that things work the way they want it to work. And so it's a change a little bit of how you think about it. And I mean, this kind of derives from this. There's no guarantee. There are no guarantees about the order of messages. So you invoke ABC on an actor. We send the messages ABC. Not necessarily the actor will receive them as ABC. There are no guarantees. The messages themselves, what you send as a message to another actor, it should be immutable. It's a piece of data. It's not references. You shouldn't, as in, I think, good practice in OOP, you shouldn't call by reference things and pass by reference some parameters. Same in actors. You should send messages that are data, that's immutable. Nobody can touch it on the way, and doesn't reference anything else. It's just all of it. Say like a RESTful way. You send an HTTP request that has all the data in it. That's it. The server doesn't need anything else. So good. So far, so good. Yeah. Now let's try to write an actor. I will write now a counter actor. I'll give you a second to just read it and figure out for yourself what's going on. Can anybody sum it up for me? No? Too hard? Sir?
You receive the message increase.
Yes.
You take the increment count.
Right.
You receive gets. You send to the sender count. If you receive anything else, you print another message.
Cool. Exactly. There are a few little parts here. First, here, this is what the message. Look, I'm pattern matching on the message. Because the message is data, remember? The messages are data. So I can pattern match on them. Regardless of the type. This is the cool thing. The type is what's going to be pattern matched as well. So if I receive a message increase, I'm going to count +1. When I receive a message get, the sender, this is a method inherited from the actor. So this is the actor framework I'm talking about, ACA. And whenever you want a class to be an actor, you just extend actor, and then you have access to many utility methods that are useful here. So this sender gives me the address of whoever sent me this message. And with this address, I can say bank count. So this is the way to express send a message. So address bank message means send this message to this address. And if I default, so I couldn't pattern match these things, so I do not understand the message, I say unknown message. Here probably you log it in some system somewhere, and you debug it later. You create an alert over the log and you debug it. And this is what we meant by when I receive an increase, I receive a message, Oh, look, with this message, I sent messages to other actors. With this message, I designated myself for the next message, meaning I mutated the states, such that the next message that says get or increase will deal with the new state. Okay, so this is stateful counter. We have a state and we mutate it, which is fine, This is completely okay with OOP. If you're coming from OOP background, this is exactly how it should be done. The functional people will go, no state. It's just too much. A counter, an integer, no, this is too much. There's another way. I define, you took functional programming classes or something. You did. Who knows what a partial function is? Partial function. Doesn't ring a bell. Okay. Okay. Let's take a look at this. Okay. If I take this one out, okay, there is no default. This is out. This function that we call it receive is a partial function. Why? Because it doesn't work on the whole possible input domain. It works only when the input is increase or get. For the rest, it doesn't work. In other terms, when you have a method in Java, let's say you have a method in Java that takes a parameter of integer, but it expects a positive integer. So not all integers. It will not work with all integers. That's a partial function, mathematically speaking. It works on a subset of the input domain. This concept, of course, in Java, I can make sure that I throw an exception when the thing is out of boundaries, or I return some error message, or whatever. In functional programming, you can explicitly say it, explicitly declare it. And this is how you do it in Scala. You define your method or function like that. You immediately start pattern matching, meaning that whatever the input is, one input, by the way, I'm going to pattern match it with this and do the following logic. Otherwise, I do nothing because there will be an error. So now this is a bit more tricky. I will define a count method that takes in an integer and returns. So count takes an integer and it is a partial function. Look at it. It starts immediately with pattern matching. And here, whatever, if I receive get, the same. I'll bring back the n again. Look, there is no state here. The n. I'll send back the n to that sender. But if I receive increase, what would I do? Context, again, coming from actor. This is utility for you. You say become count n plus 1. Context is a stack that you can push partial functions in it. Think of it this way. It's a stack of partial functions. First, this is the receive. First, it's count 0. So the first partial function now is count 0 in the stack. So if I receive a get, this is 0. See? 0. So I will send 0 back. If I receive an increase, I will say push count n plus 1. So I'll put count 1 on the stack. The next get, what will it get? It will get the 1, which is from count 1. And this is the functional way of doing things. Of course, whatever you're comfortable with, there's no preferable way of doing things, but I just wanted to bring an example of how it works.
What I don't understand here is the n is explicitly declared as
Yes.
parameter, but the string so that is not.
It's implicit in the receive because the receive is a partial function from n to unit in Java world from object to void. Meaning, whatever I'm pattern matching here is the message, is the input. Okay? And the N is explicitly set in the parameter.
So can you pattern match against other kinds of objects than strings?
Of course, and next examples will be this. Data. I will pattern match with data. It's a style. So I've seen people going crazy about functional ways of doing things. And I also have seen people so religious about the OP style. But to me, there's no preference. Whatever fits the problem, expressing the problem that you're having. Work with whatever makes it easier to read, makes it faster to perform, less prone to errors. So you have to think about it this way and don't take hard opinions on it. Okay, now I want to work with this actor. Okay, I have a class that extends actor. Now I have to instantiate it and make an actor out of it. How do I do that? Again, this is Akka, the framework I'm talking about. You instantiate an actor system by saying actor system, you give it a name. So now I have an actor system. I have an environment where I can put actors in. And I would say counters, you don't instantiate actors as objects of type class of some sort. No. You tell that system, hey, create an actor that follows the counter class.
There's a question on the chat.
Yes.
Akka actors are still untyped? Were they untyped once? They're typed or untyped?
What does it mean? They are absolutely typed. Yes. Yeah, so the actor we see, this actor, it's of type counter. I mean, of course, you can send it whatever message you want. So in that sense, it's not a typed class. No. An actor, you can send it whatever you want, and it's on the actor to do whatever it wants with that message. So in a way, they are kind of detached. I'm not invoking a method. I'm just sending a message. And this is how you send a message. Hey, counter. Increase, get, done. You follow me? All right. A little bit of motivation also why actors are cool. I've seen recently a lot of web applications written in actors. It's a cool way to handle multi-threading in your web application. For example, in Scala, they have this framework called Scala Play. It's written on top of actors, and you have access to that actor system. Meaning, if you want to spawn threads, you spawn actors in your actor model. In your backend, you have access to the actor system. And you can do whatever you want. Like whenever somebody says something, okay, here's an actor that will write to the database. Here's an actor that will send this message to, I don't know, this customer, and so on and so forth. So this also makes it a lot easier for you to do web applications. Ping pong. Let's do ping pong. So I'm going to create two actors, a pinger and a pointer. And they just send ping, ping. Okay. The imports of the framework objects. Anyway, case object ping. So what is that? It's a data object singleton. I have one. I have the ping. Just one pinger. Case object pong. I have another one. It's called pong. Right? It has no data. It's just I create something called ping. And now let's create the pinger. So these are the messages. The ping and pong are messages. They are data. Now the pinger is going to be an actor. So it sends actor. I'm going to make it from 0 to 5. So ping pong, ping pong, ping pong. Somebody should keep track of the ping pong game and finish it when we reach the countdown 5. Right? Or when the countdown 5 reaches 0. So this is the pinger. So the pinger, what does it expect to receive? it will receive a pong. It sends a ping that receives a pong. So when I receive case pong, and this is for you, Oscar, you asked about this. It's a case of it's on a data class. So I'm pattern matching the pong. If I receive a pong, all right, I will say receive this pong. I will bring, if I receive the countdown 0, if I don't receive the countdown, if the countdown doesn't reach 0, I'm gonna decrease the counter and send the sender ping. I receive a pong, send a ping. Otherwise, this is cool. If we reach 0, what do? We need to finish the whole thing, finish the game. How do we finish the game? I send the sender a poison pill. And this poison pill also have access to it. You see it? It's in the imports. It's a utility also data object. Every actor knows what to do with it. It just dies. So whenever you want to kill an actor, here's a poison pill, dead. Yes? And then commit suicide. So self-poison pill, take it, done. This stands for Romeo and Juliet thinking. So what does the pinger do? Whenever I receive a pong, send a ping, pong, ping, 5, 6 times, send a pill, take a pill, die. The ponger is a little bit easier. The ponger, whenever it receives a ping, it sends a pong. So one actor is responsible for ending the game and managing the complexity of the countdown. The ponger doesn't do anything. Whenever it receives a ping, it's a pong. The ping pong application, again, we need an actor system, right? We instantiate one. We need actors, pinger, ponger, and here how we do with them. I say, here's the schematic of the actor, and here's the name of the actor. Because you can create several actors following the same schematic, but with different names. And you start by sending a ping to the ponger. Hey, ponger, ping. And this is the game. Ping pong, ping pong, ping pong, dead. And the system is over.
We go back like 2 slides to where we send the poison pills. If we were to switch the order in which we send poison pills, would the outcome be deterministic in that either always we would die first before we get sent the second message, or would we open ourselves up to a race condition where, depending on how long the message takes?
You don't open yourself to anything. Remember, it's on you. You are sending the message. There are no guarantees. These are asynchronous. So it's going to be okay. Send. Okay. Now, if you first killed you before sending the other one, that's on you. You are the client. You see what I mean? So there are no guarantees about the order or about the delivery of the message. You see? So I have no answer. It could be either way.
But then that means that it's not really safe. So you could technically kill yourself before you kill the other one.
Now let's think about it a little bit further. An actor can process one message at a time. Right? So when I send myself a poison pill, it's going to be in the mailbox. Right? So I'm still processing this message. So I'm going to send the sender the other one. Now, the order means that I don't know which one will die first, but I don't think there's a race condition.
But it's not possible to kill yourself before sending the message, because you just send yourself a message and that's the back of it.
Yes. Right. Anything else? Okay, let's do something a little bit more interesting. Now it's going to get a little bit a notch higher. This is how we approximate pi with a series. Yeah, it's a Leibniz formula. It's fairly simple. So if we break it down like this, so pi will be 4 multiplied by this alternating series, or whatever you call it. So 1 minus 3rd plus 5th minus 7th, and that's it. And the accuracy of this, of course, depends on how far you want to go. Yeah? Okay. How do we parallelize this thing? What would you do if you want to build a multi-threading application that you have like has a supercomputer, has 1,000 CPUs, each one has 1,000 cores, all right? And you want to reach as much as you want. What would you do? So the thinking of parallelization is the same. Whether you're doing multi-threading, multi-actors, distributed systems, it's the same. Okay, I have something big, I need to bring it down to little pieces and send these little pieces to workers or threads or actors. It's the same mentality, yeah? So we think, okay, how about we do this? We think this is an element, all right? And I'm gonna send these computations, as many of these elements, to different actors, meaning, I'm gonna do this. This is my system. Oh, sorry, here there are workers. And there's a master. The master will receive a message from the client of the actor system saying, calculate pi. So give me an estimation of pi. The master will distribute the load on different workers, probably several times. So whenever a worker finishes some job, send him another thing, then another, then another, all right? Then collect back all the results. Do the final calculation, which is sum it up, and send to the listener, which is whoever is interested in the approximation, send in the pi approximation. Yeah? Should we do this? So let's look at this. It's going to be like that. Each actor will receive a payload of a job to do. And this payload looks like that. So, hey, worker 1, calculate this. Worker 2, calculate this. Worker 3, calculate this. Because I have 3 workers. The next message will be for worker 1 again. So that's kind of a round robin style of distributing things. So next message, and I move on. So what are the configurations of my system? What do I need to specify? How many workers? Depending on how much your system architecture is big. Number of messages, meaning how far I want to go with this series. And number of elements for each message, meaning it's probably wasteful to send each worker just one. Give me this there. Maybe each worker can receive 5 of those elements, and the next worker, the next 5. The next worker, the next 5. And then how many 5s I will send is the number of messages. You got the idea? So the messages are how many payloads I will send to the workers, and the number of elements per message, how many of these each worker will calculate. So let's start creating things. As usual, as in OOP, you start by building the data structure. Always start with the data structure. This is a good advice I got at some point when I was doing interviews. Whenever you are doing an interview, somebody asks you, we have this thing that takes in an array, takes in an node, and then calculate to me this, and that. First, start what is the best data structure for the problem. This is your first step. Interview, building a new system, debugging, what is the data structure? Figure this one out, everything else follows. So now, data. I want all my data, so this is sealed trait, pi message. traits are like interfaces, but a bit more in Scala. So in traits, you can have pieces of code that work. So it's a bit between abstract classes and interfaces. But for me, this is a data trait. So I'm gonna label all my messages in this actor system as a pi message. It's a pi message. So the first message is calculate, extends pi message. The other message is, second message is work, which means it takes a payload of from and how many elements. I'm going to go back a much. So from how many. And this is the work message that I'm going to send to an actor. What is the result? It's a double. So the actor was just going to calculate it, send it back as a double. Also, it's a pi message. And the pi approximation, what is it? It's the final result. Plus, I added one up, how much it took me to calculate it. All right. And this is how it looks like. The calculator comes from the actor systems, which is how I initiate the whole thing. The master will send work messages to the workers. The workers will bring back results. And the master then will send to a listener, which is another actor, that will just see the message and probably print it or do whatever it wants with it. Let's start with the worker. It's nothing really fancy. Calculate pi 4, again, from number of elements. And it's just a for loop of summing things out. This is exactly what you see in that form. Okay? For I from the start until the end of elements, do this accumulator, and this is the result. So in Scala, you don't say return. Don't need to say return in a method for it to. It's the last instruction. So what is the last instruction? Act. What is act? It's actually a var which looks like a double, so it knows immediately that it's a double. It returns it, and this is so here you can say return act, but you don't have to. Okay, so this is the logic. This is the behavior of the actor. Huh? Now, what is the interface to receive messages? I have to define this method, receive. Case work from, for how long? You see the pattern matching magic here. So what I pattern match is the type of the message, just the type. If I receive a work, good, I know what to do. I extract, I get the start, I get the number of elements, and I send the sender bank this logic. Easy? And let's finish this one, then we take a break, okay? Sorry. Now, what does the master do? The master needs a little bit more. It needs all the configurations of the system that I want to. Number of workers, number of messages, number of elements per message, and give me also please give me the mailbox actor reference of the listener. So when I have the result, where to send it? Give me the mailbox of the listener. So first part is I said the configurations, and here there's a story twist. So the listener needs to send messages in a round robin manner. 1, 2, 3, 1, 2, 3, right? I can do that. Probably I can have like a for loop, a little bit complicated to see, okay, which address, which actor, blah, blah, blah. But I don't need to. So I can, as I said, in the worker, I can create 3 actors based on the number of actors I have and make a round robin myself. But again, the framework comes with some utility actors for you. And that utility actor is called router. So I say, okay, create an actor, a router actor that can route to 3 workers. It's a little bit convoluted, but this is how you're going to read it. So what's going to happen is that we were like this, But we thought, okay, let's make it a little bit easier. Let's do it like this. All the messages from the master going to the worker, from the master to the worker will be actually sent to that router, which is yet another actor, because everything in an actor system is an actor. So the router is yet another actor, right? Here's it is, and the router would know what to do. It's a router. Simple enough until now. Okay, now let's define the receive. Again, how do I interact with the outside world? Huh? I receive a calculate. Good. I iterate from I to the number of messages, and then I would say send work messages to the worker router. Work. Like that. And when I receive a result, so remember, for each work message, we expect a result message. So when I start to receive a result, encapsulating a value, I add it to my base counter, which is 5. And when I reach the number of messages that I designated my system for, okay, now it's time to finish the whole thing. Huh? So I will figure out the current timestamp, because the start timestamp I did it when I first received a calculate, and the end timestamp is when I want to send back the result, the final result. Calculate the execution time, and the listener, I have its mail address. I send it the pi approximation with the information I want. And this is something else. Now I say context, which is coming from the actor, dot stop self. What does it do? So this is the master. Huh? The master is the one which created the router. So in actor system, it's called its supervisor. So this one supervises that one. And the router created the workers, so it supervises them. When I say context stop self, what will happen? It will propagate. When a supervisor dies gracefully, like I'm doing it intentionally, it also propagates the death to all its supervised actors, such that I don't have any leftover in my system, and I make sure that I go in peace. So this is what it does. So what is the listener? It's nothing but a receiver of the pi approximation or the final result. Hey, whenever I receive it, give me the print out the thing, and context.system.shutdown. Okay, now bring the whole system down. And now the actor system is all out. This is the app. As you imagine, I create the calculate message, right? And master.calculate. And this is the boilerplate now. I create an actor system, create a listener, because I need its reference to send it to the master, right? Remember, the master needs a listener. This one. This is the address. Create the master and tell the master start. Final words. You see, we didn't say anything about concurrency, did we? Actors, and we send messages to them. There's nothing more. So the logic of how threads are assigned, how things are happening in the background, I don't care. I just write my own business logic. This is the whole point. And remember, actors send messages to each other. They do not invoke methods, send messages. So in theory and practice, an actor could live in another machine, and its address it's a IP and port. I just send the message to it. It's totally fine. So it's not my job really to say how we receive or send messages. It's the framework's job. So if you create an actor on another machine, sure, the system will deliver the message to you. Best effort. In a way, scalability is a deployment problem, as I said. How you deploy the thing. Of course, the modeling is like OOP. This is what I just said. And fault tolerance can be implemented on top of this, meaning each actor, as I said, could be supervising several other actors, correct? And it has a way to see, are they alive? Are they not alive? And if they're not alive, create another actor. And this works beautifully, if you want to build a distributed system. I hope I got you excited enough about actors. You can, after the break, 10 minutes break, we can go to the Spark. All right, so we're going to talk about Apache Spark. What are RDDs? What are DAGs? And then again,
Do you want to ask the question from the chat?
I did. They weren't there.
Oh, now that we're back.
So, okay, what do? I just say.
Yes.
Okay. So there was a question in the chat about the actors being not typed, meaning that you can send any message to any actor. That is true. And the receive function is from any to unit, which means from, you can send it anything. That is also true. In your system, it is typed in the sense that you know the types, so you can check things, right? The type checker will do some work for you. In the running system, there are so many unknowns because any actor could send anything, and that is true. If your actor system is grows a bit bigger, you are prone to messages being ununderstood, right? Not understood. It's not particularly a problem of the actor systems. It's a problem. It's a known problem with the partial functions. How do I make sure that it's a problem even in OOP? How do you make sure that the input is exactly what you expect it to be? You need to assert things, preconditions and post-conditions. It's the same thing, the same family of problems. One way to deal with it is to have you could have a default, as I said, case underscore. That's okay, the default. If a message I don't know, don't die, because if this happens, you throw an exception, probably the actor will die. But you can have this, don't die, just don't do nothing. And it's on the client side to figure out what's going on. Not my problem. I do not understand the message. There is no universal solution because it's really problem dependent, context dependent. Okay. Spark. When people tell you that academia doesn't produce good stuff, tell them you don't know nothing. All the cool stuff that really came to industry came from academia. One of them is Spark. It was a PhD thesis of a student, Berkeley, if I'm not mistaken. It was all about, okay, how do we design good distributed systems? His PhD thesis turned into a framework. His framework got adoption. People liked it. And we have now Spark in millions of applications. It was about big data. How do we handle big data? And big data, one important characteristic of big data is that there are no rules. Data could be database sources, nicely structured records that we know exactly what attributes were. Could be semi-structured, something I can parse, maybe like a log file or something like that. Yeah, I can know how to parse it, or something completely unparsable, like a file. And you have to really have special ways for special cases. I know nobody talks about big data anymore, but you know why? Big data was hyped 10 years ago, probably. Now, not anymore. But you know why? It's really interesting. It's because now the norm of what data is. There's no small data anymore. Nobody tells you, yeah, you know what, this little MariaDB or I don't know what, MySQL DB, and that's an application, that's it. That's rarely the case now. We expect data to be dirty, big, different formats, different speeds. That's now the norm of expectation. This is the world we live in. So big data is just data. I don't really talk about it anymore. So Spark is a data processing pipeline framework. Just read data, do processing in a distributed manner, produce output. It has the following architecture. High level, very, very high level architecture. Remember what I said? The logic of how distributed systems or parallel systems or concurrent systems is pretty similar. You have a driver, like the master in our example, and you have workers. You send them tasks, you gather results, here you go. As simple as it gets. Spark, or that guy's, I forgot his name, that guy's PhD thesis was not about Spark per se. It was about, again, remember, data structure. What is the data structure that really suits distributed computations? And he came up with this idea, resilient distributed data set, RDD. It is a partitioned collection of records. Let that sit for a bit. Partitioned collection of records, meaning I have university employees. That's a lot of records. And I would say, all right, all odd numbered IDs are on this server, all even numbered IDs are on the server. So what I did, I took this whole set of features. Based on the IDs, I partitioned in the data set. So it's a partitioned collection of records. You control how you partition it in the best way for your application. Probably based on the ID is a bad idea. Don't do that. Because IDs have no meaning whatsoever, right? Maybe I want to partition the university employees by address zip code. That's important, more important. Later for processing. RDDs are read-only, they are immutable. This is also a big important feature. I cannot go in the RDD, hey, set this value to this. No, you have to create another RDD with the new value. And RDDs have this nice way of flowing. Can only be created through deterministic operation. Through a deterministic operation. You have something to say? Oh, sorry. Data from stable storage, meaning data is in a database, in a file system, distributed file system, server, remote server file system, I don't care. It's in a stable file system. I can create it from there, so read, that's my RDD, or from other RDDs. Meaning, okay, I take this RDD, I do something on it, it became another RDD. Why do I do that? This is an example of what it means to have a DAG, a directed acyclic graph, or computation graph, if you want to go hardcore computer science. It's a computation graph. Meaning, this is my RDD. All of them, it's partitioned. You see how it is partitioned? So when I read it into another RDD. And I do a transformation, and that results in another RDD. So just follow the legend. This is transformation, and that is an action. You see it over there. What are transformations? What could be? For every record, let's say, for every record of my feature data set, I want to capitalize their last name, make it capital case. That's a transformation. That's a map function. So I map each record to another record. So map is a transformation. filter. I can filter this RDD by taking only the people in zip code 3012 Bern. So obviously this RDD is smaller, but it's another RDD. Of joins, filters, maps, flat maps, all that, those are concepts coming from functional programming, if you know functional programming, and they are one-to-one applicable here in this sense. So all transformations can be applied to one RDD and result in another RDD. Then when do you get actually the data? When you perform actions. So say, yes, okay, capitalize the last name of each employee in the university. Good. So what? Now what? If there's no action, my map function has no meaning whatsoever. One action would be show them to me, print them. Okay, that's an action. Save them in another database. That's an action. Count them, distinct them, do something such that it results in an action. And this is what I mean. Only when there's an action, then I get results. Up to this moment, all this is lazy build. Meaning, actually, if you say RDD1 dot filter when zip code 3012 Bern, and you send this job to the server, nothing will happen. Because what's the point? You read from this, you say, okay, filter on zip code, and then what? If you don't say then what, nothing will be executed. The DAG, directly acyclic graph, is lazily built. So whatever you specify in your Spark application will be just used to build the DAG. We build it, then we send it to the server, and the server decides, oh, you know what, there's no action here, I'm not doing anything. Or if there's action, let's do something. Another interesting thing. Yes.
Is the server smart enough if you specify some transformation that's not needed for your action that it won't execute?
This is the optimizer, the DAG optimizer. It's the job of the, it's a special thing in Spark that will figure out the trivial stuff, yes. So if you have a line of transformations with no action that's trivial, it will figure it out. There are a little bit of more complex stuff where it can merge transformations together to do it in one step. It can do that, but of course you have to help it. You have to express your DAG well enough. Now here's the cool thing about RDDs written and specified in this way. Say the machine that was responsible for this partition died. For some reason, out of memory error, power outage, whatever it is, this machine, go. Okay, what do we do? Well, I know the master server, it has heartbeats with the workers. I know, okay, this worker died. Probably I should recalculate whatever this worker was working on. And it has the lineage of the RDD. Because RDDs, if you remember, come from stable storage. So the origin of every RDD is stable storage. Meaning what I can do, this died. I go back on step. Do I have this? Oh yeah, I do. Okay, good. Then assign it to another worker and do it. And then reattach again to that state. And this happens all behind the scenes. You don't need to. You do when the failures become a little bit out of control. So you have some certain number of restarts and number of job failures that after that you are alerted. But in the normal case, this happens all the time. Network error, timeout error. I see it in my logs all the time. Sure, okay. I see that this worker died, another worker was pwned with the same data and all good. And this is the concept of lineage, data lineage. It comes from a stable source all the way to another stable source, which is when you do an action to update them. And any interruption in any way in the lineage, I can recalculate things from that exact point. Because RDDs are immutable. You see, this is the beauty of it. You cannot mutate it. So I'm not afraid. I know exactly what this looks like at this stage. And I can recalculate things from here. Let's build a word count example. I hate this example, but it's the only one I could I could make it in one slide. There are much more bigger examples, but I don't think I can do it like that in a lecture. But here I think you will just get the idea. Like the actor system, I need to create my Spark system. And this is what I do. I specify, so this is boilerplate, okay? Configuration, these are the master is a local of 2, set up name of word counter. Local 2 means that you have a master thread and 2 worker threads, because this is local. You see the configuration says local. And by just changing its configuration to yarn, for example, then you can specify the number of workers and deploy this thing. Then you have the work, each worker is actually a JVM on its own on a different machine. Spark context, which is exactly what I want now to do things. Create a new Spark context of this configuration. All right, now I have my Spark system. Every RDD starts from a stable storage. The lineage starts from stable storage. In my case, it's going to be a file, text file. So I say Spark context, the system, read the text file, this thing. And this is my first RDD. Here. File system, my first RDD, and it's RDD of type string. So it's the text file method returns, it's a utility method from the context. Meaning that, remember, it's a partitioned collection of records. For me, each record is a string, a line. Words. What are words? Lines dot flatma. So for each line, I have to break it into words, right? So I say for each line, this is the lambda function in Scala. For each line, split it. And because this split returns a collection, that's why this is a flatma. And meaning words is yet another RDD of strings, but this time a string is not a line, it's a word. Are you following? Good. Okay, I have now a huge collection of words. I want to count each word, how many times it appears. What do? I do another map to a tuple, key, and the value is 1. So for each word, for each record here, I will create this record. The word itself, coming from it, and the number 1. That's all. You'll see this, how this trick works later. Now these pairs reduce by key, meaning for each tuple sharing this key, do this operation. For each two tuples sharing this key, just sum the counts. So the result of this transformation is yet another one that looks like this. So the same type, but now it's not 1 anymore. It's the full sum of ones, the ones that appeared, meaning the number of occurrences. And what I can say is that, okay, results, word counts, this one, take 100, meaning give me 100, a sample of 100 records. I want to see them, and then I can iterate over them. So this one is an array coming from a take, and this take is an action. So only at this moment here I start executing. Before this moment, nothing is executed yet. Only I say take 100. All right, we need to calculate this. Then Spark starts pop, 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 and then it gives you 100 records as a sample, and then you can print them because this is an array. So what am I showing you here? What do you think? I highlighted only the lambda functions. Think about it. What's the difference between the blue stuff and the black stuff? Where is the parallelization actually? Where is it happening? What do the workers do? And what does the master do? It's a little bit unobvious, right? You see?
The workers can use them.
Yes. The workers work on the records of the collection or of the distributed partitioned collection, the RDV. This is what the workers do. They have only a subset of this collection and they work on it. So whenever I have a variable that is an attribute of a record, you know that this is actually happening on the worker side. Everything else on the master side. And as I said, everything that up to this moment, nothing happens. So if you run this application without this, literally no computation will be happening. Nothing. If you add this word, computation will happen. You will notice that actually the application takes more time, and then you see results. Spark has, if you know functional languages or functional programming, Spark will be a piece of cake for you to write in Spark and express your computation and data pipelines in Spark. Because you see, if you forget the first two statements, this is pretty obvious. It's just map, flat map, reduced by filter, stuff like that. This is normal collection operations, or in the Java world, stream operations. That's it. Yes.
So it's done completely lazily. Once you get the first 100 word counts, then even if there are more things to compute, it'll stop.
I don't think it's that smart.
Mm-hmm.
No, I don't think it's that smart. This happens, for example, in database systems. Yes, when you say limit the results by 10, it will really just figure out the first 10 and shut it down the whole computation. In Spark, no. It just figure out that this is okay. There's an action, or I need to compute things now. Plus, in this example, I'm not sure it can actually do any partial computation because of this reduced by key. You need to make sure that you have to collect all the results from all the workers to make sure that actually, yes, for each key I have the result. Questions? All right. As I said, so this was at some point powered by actors, not anymore. You have other systems, other frameworks for big data computations and whatnot, like Apache Flink, for example. As I said, it's kind of a successor of Spark, works on similar theoretical concepts. You have Kafka Streams, if you ever heard of them, works also on the actors. You have websites, web applications working on the actors, because it's just easier to express my problem in actors. Here, I don't even see the actors. I don't care. But they happen in the workers. Okay. Few references. So these are the ones that I used to prepare this lecture. They are pretty. I really would like you to look up the guy, Carl Hewitt. Look up his lecture. He's a cool dude, very, very cool. And whatever he says about the actors can be, you can really reflect and think about computer science in general. He's really a good teacher. And as an exercise, I'm not sure if this is mandatory or not, but this is up to you. I gave you hints on what actors are. So my hunch is that you can build your own actor system. You know now exactly what an actor is. You know exactly what are the constraints, the expectations. So go ahead and build your own actor system in Java. very simplistic, and re-implement the 3 examples I showed you in that system, in your own system. It's a pointless exercise, but still an exercise, like going to the gym, right? Okay, that's it from my side, guys. I hope you like it. If you have questions, please.
Thank you very much.